Excellent. So today we have one talk left, and we're starting a little bit late, so you should go on for a little bit longer.
I won't.
You're all that's standing between us and wine.
Exactly.
Let's not dwell on that. So our final speaker for today is Jeanette Janssen from Dalhousie
Yes.
University, who will be telling us about random networks that come from an underlying spatial process like this.
Yes, thank you very much, and thank you to all the organizers for the invitation. Already it's been a very interesting workshop, and I'm looking forward to the rest of the week. I especially enjoyed the talks by Jennifer and Christian, because my work is to some extent based on their work and the work they presented. So that was very nice. I can actually skip over some of my slides. So I will finish well before the wine. So, I became interested in applying my background as a graph theorist to complex networks about 15 years ago, when a colleague from computer science pointed me to the papers that appeared just then by Broder et al. And by Barabasi and Albert, where they first analyzed the network underlying the World Wide Web. Well, in those 15 years, of course, this whole idea that the link structure, the connections between entities, can tell you something about those entities is not new anymore. It has been extended from the web to networks on the web, social networks, to networks in biology. I really like the work that's being done on the connections between neurons in the brain, the so-called connectome, and I hope that graph theoretic methods will eventually be able to be of use in there. In ecological networks, there is a group of researchers in biology in my university that looks at networks of bacteria in the gut and tries to see by the connections they have whether they inhibit the occurrence of certain diseases. But while there are now a whole suite of network analysis software, etc., the tasks are still mainly focused on two questions. Extract communities from your network, where that's usually defined as, well, some kind of densely connected subgraph, and given a certain vertex, can you find other vertices that are like it, that are similar to it? And those two basic tasks, they implicitly assume that reality that they're trying to extract is already there. It's not a community because it's densely linked, but it's densely linked because it's a community. So there is an underlying reality, and that gave rise to the graph, and you want your whole idea with this link mining is that you want to extract that underlying reality. So then it's very natural to represent this hidden reality by the positioning of the vertices in a feature space. And we know from data analysis that feature space doesn't have to be, even if you have many features, you can probably represent the same reality in a very low dimensional space. So, okay, and then what does it mean for this feature space, the position in the feature space to represent that reality? That means that somehow there should be a relation between the distance in that space and the occurrence of a link. So vertices that are closer together in the space are more likely. Okay, so what I want to present here is a very general spatial model, which is exactly the model that Christian presented, namely based on graphons, where the graphons are spatial graphons, so they have that property that vertices closer together will have a higher probability. And actually, after defining that spatial model, I'll immediately go to the simplest possible case, namely one dimension, the line. But I'll also indicate how the ideas can work in higher dimensions as well. First, there is actually the certain linear graphons which have a nicer structure, a certain uniformity, and I will describe how to recognize those. And I will also define a graph parameter that will identify a graph sequence that converge to a linear graphon. And then I will also look at retrieving that linear reality in terms of the ordering of the vertices on the line, and I will illustrate that with one particular example. Okay, so what is the general spatial model. I have slightly different notation than Christian, but it's the same model. So G n comma W, where W is a symmetric measurable function from S cross S to 0, 1, and S, that, in this case I'll just consider to be bounded and convex region in k-dimensional space. So I draw my vertices uniformly at random from the space, and I connect my vertices with probability given by that graphon, Wxi comma j. Okay, so far so good. So this is totally general. But I wanted this property that in general, when points are closer together, they are more likely to be connected. So I'm expressing this with this probability, with this property here, that if I take a cutoff threshold, say probability A, and I fix one particular point in the space, then the region where all the points live that have probability greater than A should be a convex region around X. But that region could be, it doesn't have to be a circle. So this means that as you walk away from X in a straight line, the probability will decrease, but it may decrease in a different way if you walk in a different direction. And the motivation, of course, is that why take this particular model, because then we can apply this whole nice theory of graph limits. And especially what I want to focus on is this: we have this convergence in this cut distance space, etc. But that also is equivalent to convergence in terms of these homomorphism densities. So homomorphism densities, some kind of generalization of subgraph counts or motif counts, very often used to characterize networks in biological networks, etc. So what's the proportion of sets of 3 vertices that are triangles, etc. So if for every small graph you know what the homomorphism density is, then you have a very good idea of what the structure of the graph is. Indeed, there are certain graph properties which cannot be expressed in terms of homomorphism density, but still they give a very good idea. So what you have then, suppose that you have a sequence of graphs for which these homomorphism densities for one particular small motif f, they all converge. Well, then you have very much reason to say that all the graphs in this sequence have the same structure, and that structure gets more and more get closer and closer as the graphs get bigger and bigger. And it then turns out that in fact you do have convergence in that case, in that sense of convergence to a graphon. So to repeat a little bit that theory, so if we map our graphs to the space of functions, which we can do by just identifying, cutting my S up into equal size regions and mapping those to basically the vertices of the graph, and then we equip the W with the cut norm. Jennifer presented it in terms of matrices, but you could just as much do this with an integral and have the continuous equivalent. So you take the supremum, so the cut norm is you take the supremum over all 2 measurable sets A and B of the average over A and B, A cross B. So then we have that nice theorem that yes, sorry, that is one typo that I didn't even guess. So then we have that nice notion that in fact convergence in the previous terms, so convergence in structure, let's say, convergence in terms of homomorphism densities, exactly corresponds to convergence in this cut norm, or the distance derived from it, except that, well, you may have to permute it depends on how you label the vertices. So there is a way of labeling the vertices, or of permuting the vertices, so that the corresponding sequence is Cauchy in the cut norm. And then if you extend that distance, that cut norm, to a cut distance, where you take you basically take all the graphons that have cut norm distance 0 to be an equivalence class, then you have a compact space. So now your graphs also converge to a graphon, or actually more accurately a whole equivalence class of graphons. Okay, so what is the important thing that I want to take away from this? That if you have such a sequence and it converges to a certain graphon, then the graphs of that sequence really look like typical graphs that would be produced by that random graph model Gn, W. So if my, so coming back to this, this whole idea, so if my graphon, my limiting graphon, is a spatial graphon, that means that the graph in my sequence are consistent with having been produced by a spatial random graph process. Okay, so that was the general setting. Now immediately back to down to one dimension. So what is if our set is just one dimensional, and it needed to be bounded, so let's take it to be the interval 0, 1. So in that case, talk about a linear graphon. That same definition of spatial still holds. In this case, the region, so if you take a threshold A and you look at all the places where W has value greater than A towards a fixed point X, then this has to be now an interval. But we can also formulate it in a different way. We say if we have 3 points, X, Y, and Z, and X is less than Y is less than Z, then, well, X and Y are closer together than X and Z, so W, X, and Y must be greater or equal to W, X, Z. And similarly, W, Y, and Z are closer together than X and Z, so W, Z, and X must be less or equal to W, Z, comma, Y. And that's an equivalent way to define spatial in terms of one dimension. Here's some kind of example, actually taken from a tutorial on a way to seriation in R. I'll come back to seriation.
Does this imply that the degrees are monotone? So if you integrate out one of them, it's a monotone function of the other, or does that not imply?
It's if you fix one, it will be monotone up and then down. So it will be unimodal.
The degree or the
the degree.
Integrate
No, the degree is not. The degree is not monotone. No. No, that's right. What can you say that's monotone?
So it's unimodal, you say,
if you fix X, yeah, that's what it will look like. And here in, for example, in this function, this would be a linear graphon if pink is the highest value and blue is the lowest value. So as you go towards the diagonal, either horizontally or vertically, you will go towards the higher values. But it doesn't have to be, again, it doesn't have to be uniform, so it can be different here than there. So it doesn't necessarily depend only on the distance. It may also depend on where you are in the space. And here, well, I cannot truthfully say that this was the motivation, but in working on these linear models, I did find 2 particular instances where actually linear models are used to model certain things. One is in ecology, specifically in food webs. There is actually Williams and Martinez formulated a model which they called the niche model, which has become quite popular. And I saw Martinez give a talk about this. Basically, it's a very simple model where they place all the species on a food chain line, and whatever a certain species eats is represented by an interval on that food chain. So it's not, since not all species eat themselves, it doesn't correspond exactly to the previous, but at least it's an example of a linear model. What they do after that is they actually put predator-prey equations across the edges of that network, and then they simulate and see what happens if you get a disease in one species. How does that affect the species that eat them, etc. what happens with invasive species, etc. And another linear model is seriation. So in this case, this is something in archaeology, so you may have different types of archaeological artifacts, for example pottery, and you know that certain types co-occurred because you found them together in the same layer, in the same dig, etc. So what you want to do is you want to place these things on the timeline. That's your linear model. And as I was looking into this a little bit to get some reference, I found out about Sir Flinders Petrie, one of these Victorian gentlemen, an archaeologist. He dug in Egypt, and he lived for 2 years in an Egyptian tomb. This is him there outside his tomb. But apart from having this kind of Indiana Jones type of personality, his father was a surveyor, and he may be credited with the first one who brought the scientific method to archaeology. He actually made like little strips that represented the types of pottery he found in a grave, and then he lined them up to kind of do seriation in a scientifically...
Are you saying that when we cite block methods or graphons, we should actually cite Sir Flinders Petrie?
Possibly. So now back to the simplest possible linear graphon, just two values, let's say 0 and 1. So wxy is 1 if the distance is less than d, and 0 otherwise. In that case, your graph gn comma w has a very simple description as well. Just pick your points uniformly at random from 0, 1 and connect a pair if and only if they're within distance d of each other. And if in this case we were not working in the line but in, say, 2 dimensions with Euclidean distance, then that would be exactly the random geometric graph. And the resulting graph is a unit interval graph for any graph theorist in the audience. So it has a very clear linear structure. Okay, but this also has this example had a special property that the w value didn't depend on the position. I said in my general definition that was allowed, but the example didn't have it. And it so happens that some linear graphons may have that property, but in disguise. So it may be that there is an injective embedding function pi, so whereas w cannot be formulated as a function of the distance between x and y, if I map my interval 0, 1 according to this mapping pi, then my w can be formulated as a one-dimensional function of the distance not between x and y, but between pi of x and pi of y. So the first question I want to address is, okay, so if I have a linear graphon, how can I determine whether it's really whether it's a uniform linear graphon in disguise? So can I see if there exists an embedding function and a probability function so that my w really is can be formulated in this simple way, so only a function of the distance in this transformed universe? Because also in this case the random graph gn comma w has a nice representation, because it just means that you don't sample uniformly, but you sample according to a distribution which is given by pi. The cumulative distribution function would be inverse of pi. And then, if you do that, then it's just a simple, your w is just a simple function of the distance. Okay, simplest case, what if you have a graphon of 2 values again? Well, in that case, if it's linear, then all the 1s have to be around the diagonal. So the function basically is only determined by those boundaries where you go from 0 to 1. And if you cut your graphon, you fix x, then it will just look like, okay, first it's 0 up to some point L of x, which is to the left of x. Then it will become 1, and it will go past x to the right of x, it will go down at some point. And again, it doesn't have to be symmetric. So R of x could be further away from x than L of x. So does this two-valued graphon have a uniform graph? Well, what do we want to do by transforming this into a uniform graphon? Well, here is an example of a graphon. These are the boundaries, and these horizontal lines are basically points that we sampled. Then the graph, the adjacencies can be represented as follows. Here are all the points that corresponds to the place where you intersect the diagonal, and these are the intervals. So where the function has value 1. So the adjacency, according to this graphon, is nicely given by, well, this red dot is adjacent to all the red dots that fall within its interval. So what do we do by making it uniform? We want to make all the intervals the same length, and we want to put all the red dots in the middle of the interval. But we want to have exactly the same adjacencies. Well, in that case, we can only do that by wherever we have the longer intervals, we have to put the points closer together. So that's the transformation of the space. Now, again, for the graph theorists in the audience, this looks a lot like a model for a proper interval graph, and this like a model for a unit interval graph. And these two classes, proper interval graphs, so intervals of any length, but no interval is a proper subinterval of the other, and unit length interval graphs, those are actually the same class. So on the graph limit, they can always be transformed in the other form. And it turns out that this is the case for graphons as well. So for two values, well, if there is a uniform embedding, then if L of x is further away from x than R of x, then we have to somehow rectify that. Because after I apply pi, then pi of x and pi of L of x should be some distance d apart, and pi of x and pi of R of x should also be distance d apart. So if we use that, we can say, well, as soon as we place 0, let's say place 0 as 0, then I know that the right border of the interval of 0 should be d apart, and the right border of 0 has to be 2d apart, etc. So I can follow at least some places I already know what their value should be as soon as I've played 0 and given some definition to my d. So I can form these points. x0 is 0, x1 is r of 0, x2 is r of x1, etc. Then I can place those d apart, x0, x1, x2. So they now become all at the same distance d. Then the rest is I can completely determine. The first interval I map whichever way I want, as long as this from x0 to x1 goes in the interval from pi x0 to pi x1. And from then on, if I have anything here, well, its left boundary will have to be in that first interval. So I already know where that point goes, so then I measure d more, and that's where I place my point. So everything is determined. Well, that was easy. What about three values? Well, already this example shows that it might not always work, because right here the intervals are big, so that's where you would like to squeeze your shape. If you look at the purple boundaries only, but if you look at the red boundaries, they seem to, if anything, more come together towards one. So you have two contradictory constraints on your function pi, and it's easy to construct an example where that actually happened. But I don't want to keep you from the wine, so I think I'm going to skip this example. I just want to say that just in an article that appeared just a couple of months ago, we actually generalized this idea of those points that have to be at a certain place, which we call constrained points, and we formulate necessary conditions. So basically we say when do you get inequalities that don't work, and we then show that those conditions are sufficient, and show how you can, if the conditions are satisfied, how you can actually construct that uniform embedding. And this is for finite valued graphons with some mild conditions in that all those boundary functions are bounded away from each other and from the diagonal. Okay, so now I go to back to my more central question is, okay, so given a particular graph, large graph or graph sequence, how can I determine whether it actually is compatible with having been produced by a linear graph model? So a Gn, W, where W is a linear graphon. Well, we develop a graph parameter, and the aim is that it measures how close it is to being linear. And linear embedding in this case, well, since in the Gn, W all the points are chosen uniformly at random, I don't really care about the exact position, but I only care about the ordering in which they appear. So the linear reality has been represented by a linear ordering. And then we say, well, if I have 2 points, u and v, and u is less than v in this ordering, the ordering on the line, and I have a bunch of other vertices that are all smaller than u, so they come before u. Well, the same idea. Then everything in that set is closer to u than it is to v. So I expect u to have more neighbors in A than v. And my gamma is counting the violations of that rule. So that means that if gamma is small, gamma star is small, then I think that it's close to linear. If it's big, then it means that it is far away from being linear. And if we have a graph sequence, then we would hope that if that graph sequence converges to a linear graphon, then my gamma star should go to 0 if it works. And here's the formal definition. It has this, so it generalizes this property. So first of all, I take an A that's a subset of all the vertices, and I fix one particular linear order of the vertices, and now I count those violations. So here I sum over all pairs u less than v. So here's u, there's v. And then I only look at all the vertices that are in A and that are in the downside of u. So they're smaller than u. Okay, look at all those vertices. And as I said, I want the v to have less neighbors in that set than u. So this is what I expect. That the neighborhood of v intersection the downside of u intersection A should be less than the similar thing, but now the neighbors of u. So how do I count? I count whenever that's not the case. So I expect this quantity to be negative, and if it's negative, I just count it as 0. Only if it's positive, which means it's contrary to what we expect, then I get a contribution here. And then finally, I divide it by 1 over n cubed. That's the normalization to account so that I always get something between 0 and 1. Okay, but that was still for one particular A and one particular ordering. So the next thing we do is we maximize over all sets A. So A is kind of the lens which allows you to identify where bad things occur. But after that, we take the minimum overall orderings. And of course, the ordering that's achieving the minimum is the one that gives you the best linear layout. Okay, so we hope that this parameter will be close to 0 when it's randomly linear. When is it exactly equal to 0? Well, if and only if it's a unit interval graph. So when it has a very, very clear linear structure. Well, if you want to use the theory of graph limits, we better have a corresponding parameter for graphons. And we do that in a very simple way, namely just replace all the summation signs by integrals. So we have the integral y less than z. Then we take that positive thing again. So again, if y is less than z and x is smaller than y, then we want the wx comma z to be smaller than wx comma y. And when that's not the case, then we count that. But we count that only by averaging over everything in A. and this is the other part which is with everything that's bigger than z. And then finally we take the supremum. In this case we are talking we are in the continuum, so we have to take the supremum over all measurable subsets of 0, 1. Of course, so now graphs can be seen as graphons. So what we really would like is that if you take gamma star of a graph and gamma of the corresponding graphon, it should be the same thing. Well, that's only true asymptotically, and that's basically only based on the blocks on the diagonal. So in graphs, usually you don't consider a vertex to be adjacent to itself. So therefore, you get something. You get a kind of a penalty just from the fact that you have zeros on the diagonal. But asymptotically, as your graphs get bigger and bigger, they are the same. And when is this parameter 0? Well, it identifies exactly linear graphons. So that's nice. Okay, so what happens if you have sequences for which that graph parameter goes to 0? Well, indeed, we have a kind of continuity. So we would hope that if a sequence goes to a graphon W, that the gamma star values of the graphs would go to the gamma value of that graphon. Well, that's almost true, except this whole thing of permutations. If you paid attention in the last slide and you saw a difference between the gamma star and the gamma, namely the gamma star, you had a final step where you say, I minimize overall orderings. But for the continuous parameter gamma, there was no such thing. So that's what we introduce here. We introduce gamma tilde, which is the infimum over all these bijections, measurable bijections, so generalized permutations, and then this we take gamma of W phi. So this is an infimum, so it may not be attained. So what we showed then is that if you have an increasing graph sequence which converges to a graphon, then gamma star of the graphs converge to gamma tilde W. So gamma tilde, not the gamma of W. Unfortunately, that gives us almost what we want, but not quite. Namely, if you have a sequence of graphs which converge to a linear graphon, then this tells you then gamma star does converge to 0, but it doesn't imply the converse. It's not true that if you have a graph sequence for which gamma star converges to 0, then it converges to a linear graphon, which is really what you would like to see.
So what's the contact then?
No, I believe the converse is true. It's just we can't prove it. That's yeah. So in fact, I gave a talk in Banff about a month ago, which is kind of similar, and there I already said we have proven this, we only have to write it up. But then in the month we wrote it up and we found a couple of holes, etc. So talking about this a little bit, so what can we say in the converse? So suppose you have a sequence for which this gamma star goes to 0. Well, you can say that for epsilon as small as you want, you can find a phi, so that gamma, and this should be a big gamma, for which gamma is of W phi is less than epsilon. So you can find a graphon in that equivalence class which has gamma as small as you want. But that doesn't mean that there is one that has gamma equal to 0. It's an infimum. We are in the continuum. It doesn't even mean that there has to be a W which is close to your set which has gamma W. So, but that is what definitely we believe to be true. So what we really would like, suppose that you have a graphon and that has a very small value epsilon, then we would like to prove that there is a linear graphon, so W0, so that in cut distance W and W0 are bounded by some kind of function of that epsilon. And I absolutely believe it to be true. A final thing about this is that actually now coming back to seriation, lately there has been some work on seriation, a more complicated version than what Flinders Petrie was trying to do. So basically the matrix equivalent of a linear graphon is known as a Robinsonian or Robinson matrix, which means that, again, loosely speaking, as you walk to the diagonal in the matrix and you stay in the same row or the same column, the entries increase or at least don't decrease. And the idea is, well, what if your matrix is a Robinson matrix with error? So it has that, it looks like it might be Robinsonian, but there is some error in the data, so you can't really determine. So can you then still find the correct permutation? So this matrix might also be all permuted in a way that you can't really see that it's close to Robinsonian. So how do you find that out? So our approach suggests that maybe you can use gamma as a measure of the Robinsonianness of your matrix, and if that last part of our proof goes true, it would also give you a Robinsonian matrix. So if your gamma was small, it would give you a Robinsonian matrix that was close to your original matrix. Okay, so and finally, yes, we do think of extending these notions of gamma star and gamma to the theory of LP graphons. And my collaborator Maya, who is actually an analyst, she has looked into this and she's convinced that it will work. Also, higher dimensions, well, if you use the L-infinity metric, then you can characterize a spatial embedding again by orderings, just the ordering of the x-coordinates, the y-coordinates, etc. And you can formulate that condition without referring to the actual positions of the points. So in that case, I believe that it's possible to generalize this whole approach to higher dimensions. And finally, one very quick, the last topic. So there's still a notion of computing gamma, or finding the best linear layout. Well, what if you know that your graphs converge to a linear graphon? And what if you know that they converge to a very simple linear graphon, namely the one that where wxy is p if x minus 1 is less than a half and 0 otherwise? Or in other words, if you want to put it in matrix terms, that the model matrix, which gives you the probability that every entry is 0 or 1, would just be a band matrix with an n over 2, and it would be p in the middle and 0 outside. Can we then retrieve? So clearly the model matrix has a very clear linear structure. It's easy to retrieve it. Can we retrieve the linear ordering of the adjacency matrix, which is not Robinsonian anymore, because you have ones and zeros in the middle band instead of a p itself? Let me give you a picture. So here is the band matrix when p is 0.9, so all the blue dots are ones. So here it already kind of very much looks like a Robinsonian matrix, like a band matrix. Here it's 0.5, and here it's 0.1. Now it turns out that the second eigenvector of the model matrix, so the one that has p's all here in the middle, has a very nice decreasing structure. So what does that mean? That means that if you don't know, so if you are given this matrix but in permuted form, you can easily retrieve the true ordering by just computing the second eigenvector, ordering at increasing values, and that gives you your ordering. So here, in fact, this red line here is the true eigenvector of the model matrix, the one with p. So it's actually the same function. The only difference is that the y-axis is scaled differently in these three pictures. So look at this one. So it clearly is nicely decreasing. It's actually a cosine function. So it's more flat on the top and more steeper in the middle. And the zigzag blue line is the eigenvector of the of this matrix. So the matrix which is 0, 1 valued. And you see that it kind of follows the general trend of this one. And you could imagine that if you would order the vertices according to this blue line, you wouldn't be that far off the true ordering. Well, It takes a bit of linear algebra to make that precise, but using methods from numerical analysis that are old, and also some results from Van Vu on random matrices which are new, you can put those together and actually get some hard bounds and show that for this particular example, you get the Kendall's rank correlation coefficient, which compares ordering, just the number of pairs that agree minus the number of pairs that disagree, divided by the total number of pairs. That coefficient goes to 1. And moreover, you have more precise results about exactly how much an entry can drift. It's more or less like c squared of n, so constant times square root of n. That's the maximum drift of any entry. And that also depends where. So in the middle, the vector was steeper, so there you can't have that many entries that drift too much. So we have kind of specific information about that.
So I'm astonished that the C is uniform, because if it's a cosine, I would have thought that making little errors at the top leads to very...
That's exactly. So this is overall, but we actually, I didn't want to get too technical, but we have more detailed, if you're looking at from here to here, then you have at most this many nodes that can drift by this many, etc. So this is overall, so basically including
almost
this
all
there.
vertices, I see that.
Yeah. So no vertex drifts by more than constant times square root of n, but we also have more precise results if you restrict where the vertex is located and by how much the drift is.
So with the permutation derived from x hat, you mean the order of the second eigenvector?
Yes, so you take the second eigenvector of your particular adjacency matrix, then you order those in decreasing or increasing order, and that is your approximate permutation, and then you want to see how much it corresponds to the true permutation. And we have some ideas of how to generalize this to other matrices, but we'll have to get away from band matrices. I thought band matrices would be very easy because I'm very naive, and I thought, clearly the whole spectrum must be known, but that doesn't turn out to be the case. So I think we'll go look at circulant matrices next. Those are easy.
Say that now.
Yes, I say that now. Okay, so that was just a few topics. I think there's a lot more work to do, but I don't want to take up more of your time. And maybe it's one last thing. So I realized many in the audience are statisticians. You work with data. I have not applied any of these ideas to real data. I would like to, but I would also invite anybody, if you think these are nice ideas, please do apply it to data and let me know about it. And thank you for your attention for the last talk of the day.
So you mentioned that the condition that it's linear is equivalent to the fact that it's unimodal if you fix one variable.
Yes.
So what if you looked at, instead of having the interval 0, 1, you would have the circle and ask it for unimodular? Can you do things as well?
But that's what actually we think now after this experience with the band matrix. I think that's actually an easier question, and it might be a nicer theory. It's somewhat harder to formulate this, linearity, because you have a circular ordering in some sense, which is not an ordering anymore. But I think that should be possible. So, and I think it has more, at least in practice, for that an extension of the last part of our work. I think there's more hope there. Okay.
Seems like some of the structures you're looking for would likely, in many data sets, they would be present not in the entire graph, but in a subset of the graph, right? I mean, I think so you'd be looking for kind of local relationships, and I think that's probably maybe in practice might in some cases be more realistic. I don't know if that's something that you can address, but you don't know in advance. Well, maybe you have some sense in advance where things are spatially located, so you could chunk up your data, and try to do fitting on the subsets, and then maybe try to link them together. But that's just something to think about. I'm not sure if that makes it, if it's interesting theoretically, but it might be a better fit practically.
That is true. So, for example, in that last example, you could approximate your model. What makes it a hard problem is that your model matrix is full rank. So you could approximate by a block matrix by making the blocks, big but not too big, which gives you a blocky matrix, but it has much lower rank, and then you have all the tools that you have available for the stochastic block model to do that. But I like this better, because there's no reason to cluster them in separate blocks. It just gives you a good approximation, but there's some artificiality